All right, so to continue where we left off with loops, remember that we introduced for loops. We talked about while loops as well. We had some new syntax here with the iterator operators, the compound assignment operators. And then we finished with a discussion or an example of when you would want to use one loop or another. So the takeaway generally there is that while loops are generally used when you don't know how many iterations up front that you're going to be going, and so it's some other condition. Whereas for loops are used when you do know up front how many iterations you want to go. I want to do this for 10 because I want 10 iterations because I want to count from 1 to 10. Or I've got an array that I'm going to be iterating over, which we'll talk about later, and there are 5 things in it. Well, I know that I'm going to be iterating over it 5 times. While loops are when you don't know that up front, just like counting the number of digits in a number. right? If I knew how many iterations there were, then I'd already know how many digits there are, so therefore we used a while loop. You could rewrite this as a for loop, of course, but it would be less natural, right? Because you wouldn't be reading it like you would normally, okay? All right, so to continue from there, let's talk about some common errors or common pitfalls. So consider the following, and this is only in C here. Consider the following code. What's going to go wrong here? Does anybody see anything immediately? What's wrong?
Semicolon before.
Yeah, the semicolon, right? What's gonna happen here, right? And I don't need to indent that, but you should, of course. But just to run, oops, sorry, just to run this GCC demo, right? Predict what's going to happen. Yeah, nothing, right? And by the way, it's still running because I haven't gotten back to my shell here yet, right? So what's it actually doing? I is 1, right? While I is less than or equal to 10, 1 is less than or equal to 10, do what? Nothing, right? Remember we had the same problem when we misplaced a semicolon with an if statement, right? And so while I is less than or equal to 10, do nothing and continue doing nothing. So let me go ahead and kill this. Remind me, how do we kill it? Control C, right? Let's come over here to Java and see, do we have the same problem? System.out.printf, right? And then reformat that. But if I reformat it, the problem becomes immediately obvious, right? There's nothing there. So let me undo that. And is the compiler going to warn about this? No. There's no warning. There's no error, no syntax error. It's just, it goes on forever. And I stop it there. Now remember, in C, you can use this other thing called the wall flag to warn you about things like that. And, well, okay, it should. Probably, maybe if it was like this. Come on, please warn. Yeah, there we go. So apparently it thinks that if you had the white space to go down to the next line, all right, you must know what you're doing. And says, okay, fine, go ahead and go with that. But if there is no white space there, then it says, okay, well, it doesn't guard. Just that's the exact same message that we got before, right? The wall flag will save yourself for a lot of headache if you start using it. And of course, this results in an infinite loop. The semicolon is misplaced. Control C kills the current program. Stop button in Eclipse. And then the proper use of a wall flag will catch these things. Right? Here's another one. Again, this is going to be C code initially. All right. What's the problem here? I don't even need to run this. You know, yeah.
You never add anything to I.
Yeah, we never make progress towards that terminating condition. I is initialized to 0 while I is less than 10. Print out I. We make no changes to I, and therefore we have an infinite loop, right? We never make progress, and so it'll always print 0. Right? By the way, wall flags will not catch that, right? Because it can't detect an infinite loop, right? There's a non-trivial result from theoretical computer science that you cannot write a program to detect whether or not another program results in an infinite loop on any input, right? Or it halts on every single input is how it's usually put. It's called the halting problem, and it's not solvable, right? All right, so consider the following code, all right? See any problems with that? Yeah, there's no what? There's no curly brackets. What happens in that case? Let's go ahead and copy and paste that and space over. Come on, space. There we go. All right, GCC. Run it. Oops. Oh, okay, good. Wall flag is catching it. What's it saying? This statement over here, this while, this statement, what's the full thing? This while clause does not guard this statement, but the latter is misleadingly indexed as if it were guarded by the while, right? It's saying that this I++, you probably meant to do that inside the loop, and you're not because of the lack of curly brackets. So what's going to happen here is another infinite loop where it always prints 0, 0, 0, 0. Why? Well, because if you don't have your curly brackets, that while is only bound to the first statement, first and only statement, that printf. Even though I have indented this, it's not like Python where indentation defines your code blocks. Curly brackets define your code blocks in both C and Java, right? This is what it actually is doing, right? That I++ is done after the while loop. In fact, if I did that, I don't even know if wall flag won't even catch it anymore, right? Because it's saying, okay, I guess you know what you're doing because you didn't indent that all the way, right? So be careful. Always use always use curly brackets, even if you don't need to, and use the wall flag, of course. Always use the brackets. It's good practice. Even if it's only one line, still use the brackets because the one time you forget it, that's the one time you pay for it. Okay? All right, so those are some common problems and in both languages. Let's talk about enhanced for loops in Java. These are actually for each loops. Loops without the keyword for each. In fact, there's only a couple programming languages that use the keyword for each. PHP, Python doesn't use it. Maybe a couple of others might use it, but basically it allows you to iterate over a collection, like an array. Later on, we'll look at lists and sets and stuff like that, and without having to have an index variable. So let me come over here to, this is Java only, by the way. We don't have this in C. Let me come over here and give you an array of numbers. This is a preview of what we're going to be doing in a couple of weeks here. In fact, we're going to spend, like on Java at least, we're going to spend maybe 10 minutes on arrays and then immediately throw them away because there's much better things. Right? They're called lists. Right? And anyway, we have primes here. Now I have 2, 3, 5, 7, 11, 13, and 17 here, the first 7 primes. If I were to iterate over this, I would have remember that we called this an idiomatic for loop. For int I equals 0, I is less than primes.length. That's how you get the size of an array in Java. I++. I would have to say system.out.println primes sub I. Just like we did with command line arguments up here, right? You access the first one at args of 0, args of 1 is the second one, etc. That's the same thing here with this array. In fact, that's because this is a string array up here. Okay? So here is my first loop that actually prints these out. 2, 3, 5, 7, all the way up to 17. 1 per line. The only instance that I actually used I was to actually get the ith element, though. So there's a much more compact, much more straightforward way of writing this using an enhanced for loop. And the way that you read this is for each element, I should say for each integer x in the collection primes, go ahead and print it out. Now I've already got x in my hands. I don't have an I anymore. I don't have an index variable. Instead, x automatically changes and updates on each iteration of this loop. So the first loop will loop through and print out 2 through 17. There it is up there. And then I've got another one that goes 2 through 17. That is much more compact, right? And in fact, in some instances, you have to do this. So for example, sets. Sets are unordered, and there is no ith element there because there's no first element or second element or third element. It's just a bag of stuff. And if you want to iterate over each element in that bag, there's no order. And so you have to use an enhanced for loop here. It does not use the for each keyword. Instead, it's read as for each integer x in the collection primes, ... Do whatever you're going to do with it. Okay? All right, so I'll put that in the notes. We'll revisit that much later when we're, not much later, but in a couple of weeks when we start doing arrays and collections and stuff like that. There is no enhanced for there is no enhanced for loop in C. Right. Okay, C is too old. All right. All right. The other thing that you should be aware of is nested loops. You can have a loop within a loop. Right. You do the outer loop. Right. It goes around and around and around as many times, but for each iteration of the outer loop, right, then you're doing an inner loop. Right. So you're. I can't imagine what it would look like on a track, but you'd run around the track and then you'd run around a mini track or something like that. I've never seen anything like that, but whatever. So let's come over here to, say, Java, or no, C. Let's do C, right? And let's go ahead and go with 2 for loops here. For int I equals 0, I is less than n, I plus plus, and I will define n to be 10, just to make it manageable, okay? Now inside this loop, I'm going to write another loop. For int, can I use the variable I again? Nope, because that would confuse it with the outer loop. So instead, I'll use another variable here. What should I call it? J. Why? Because it comes next, right? You see this all the time in computer science, right? So now we're learning C. You've probably heard of C++, right? Why is it plus plus? Where did we see that? I plus plus, so what's the next after C? Is C++, right? Haha, joke, right? Or anybody, a musician? So if I were to do that, what is the sharp? So if I have the note C, what's the C sharp?
Next.
The next one up, right? Up or down? Higher? Up, okay, right. That makes sense, right? But C sharp, Microsoft Java, basically. And then there's jokes like that all over the place. And in case you're wondering, yes, there was a programming language called B, and that's why they called it C. Right? So continuing with this, int j is equal to 0, j is less than n, j plus plus. When you are writing these things, be careful, because you will get in the habit of just writing it and spitting it out, right? And then one time you'll have, say, I in the outer for loops, and mostly j's in the inner for loops, but except for that one, and then it screws everything up, right? So make sure that the first thing I do when I'm debugging somebody's code is I go I, j, j, j. Right? Okay, we're good. Right? And yes, you can have another inner for loop if you want. Sometimes it's necessary, but probably rethink what you're doing, right? There's probably a better way of doing it, right? And here I'm just going to print out both. I, j is equal to %d, %d, right? End the line. But I'm also going to, I and j, but I'm also going to keep a counter here, int count. I'll initialize it to 0. And what I'll do is I'll increment this counter every single time that the inner for loop executes. So then I'll print it out at the end. Count is equal to %d. Now you predict, help me. What is count going to end up being at the end? Yeah. Why 100? The outer for loop executes how many times? 10. 10 times. The inner for loop executes how many times? 10 times for each iteration of the outer loop, right? And so consequently, we are going to have 100 here, right? And if we go all the way to the top here, you'll see that it starts out with, not all the way to the top, there we go, 0, 0. And then for each, because I is 0 on the first iteration of the outer for loop, then j runs from 0 up to 9. Then I increments to 1, j runs from 0 up to 9. I2, j runs from 0 up to 9, etc. All the way up down to 9, 9, right? In which case we've got 100. If I were to do this 100, now how many are there? What's 100 100s? 10,000, right? What's 1,000 1,000s? We call them millions, right? Let's go ahead and do it. Right? Computing is what's called I/O bound, right? If I weren't printing anything, this would actually execute in a millisecond. Right? Let me prove it to you. We're only up to the 600 anyway, so we're not going to sit around waiting for this, right? Instead, what I'll do is I'll go ahead and get rid of that print statement, comment it out, and show you that this is probably going to execute almost immediately. All right? The computing is I/O bound. In other words, it's input-output bound. That is the slowest thing that you can do in computing because it is printing out to this terminal here. Right? That is really, really expensive. Right? Computing itself of just running from I up to 0, up 0 up to 1,000, and then again another, doing a million things. Right? That's almost instantaneous. Right? But now, what if I did? Oh no, wait. So 1, 2, 3, 1, 2, 3. There we go. 1 million 1 millions. And I'm not printing anything out. How long does it take to count up to, what is 1 million 1 million? 1 trillion? Now that starts to be noticeable, right? It will, of course, it would have taken a hell of a lot longer if I was actually printing stuff out, right? And even now I'm going to kill it. But there are things, and all I'm doing here is incrementing a counter. So 1, 2, 3, 4, all the way up to a trillion. But even that trivial operation of counting by ones, when you get up to the values of 1 trillion, right, rethink what you're doing. This is why rethink what you're doing with nested for loops here. Do I really need 2 nested for loops, right? Because whatever this is, if this is x, right? In fact, if it's just n, right, I take that away. How many? What's the relationship now with count? Before, if it was 10, then count was 100. If it was 100, it was 10,000, right? So, what is the relationship? It's going to end up being n squared. If you double n square, it is 4 times as big. Why? Because 2 times 2 is 4. If you went up by factors of 10 like I was doing, right now it's 100 times slower. Okay? So let me go ahead and restore that to 10. And you're actually going to do real calculations at some point with a nested loop. And sometimes nested loops are necessary, but yeah, you should really rethink what you're doing. Okay? Generally, nesting these loops can be inefficient. Sometimes they are necessary, but certainly 3 or more, rethink what you are doing, right? There might be a better way of going about whatever you're trying to compute. All right? Any questions on loops? The basics. So your lab next week, when you start doing loops, you're going to be doing a bunch of coding kata. Have you ever heard of that term, kata? K-A-T-A. In martial arts, I'm not a martial artist, but this is borrowed from martial arts, where you're doing one movement over and over and over until you have a muscle memory of that movement, right? Like the Karate Kid, wax on, wax off kind of thing, right? That's a kata. With coding kata, it's write this loop over and over and over again until it's muscle memory, right? Or, it's finger memory for your typing now, right? But we're going to do a little bit more substantial exercises here. And I'll let you choose which one we want to do first. We have plenty of time to do all 3 of them. We could just go down the list. I could find more too. Right? Pull out the book and find some more exercises here. Write a program to compute the arithmetic geometric mean of 2 numbers. What is that? We'll look it up. Compute a loan amortization table using the monthly payment. So if you borrow, $10,000 for a car over a 5-year loan, that's going to be 60 months there, and at 5% interest. Wow, this is a fantastic interest rate right there. Or at least for today, it is, right? Then you would be paying $188.71 a month according to this formula up here. But each month you are paying part of that to interest and and part of it to principal. For example, when in the first month you owe $10,000. Now at 5% over 12 months, that means it's 5% divided by 12. That comes out to $41.67 in interest. The rest of this $188.71 goes to the principal, resulting in a pay down of that loan down to $9,852.96. You continue that. The amount that you're paying in interest actually goes down. This is why it's called amortization, because you don't actually pay 5% interest. You pay a little bit less than that because you are paying the loan down. Right? This is also the savings accounts work the same way. That's why they'll always advertise the APY, annual percentage yield, instead of the APR, because it's always going to be slightly higher. Their interest rate here for 5% is slightly lower because you are paying it down. Right? And then eventually you get down to 0. Okay? Or write a program that, given an integer n, calculates the number of primes from 2 up to n. So start at the top. Okay. So what the heck is the arithmetic geometric mean? AGM Wikipedia. AGM for short. Conditions describing knowledge and belief. Okay, that's something else completely. That's the one I want. There we go. The arithmetic geometric mean. Let's go ahead and zoom in here so that everybody can see it. So the AGM is defined as the limit of interdependent sequences Right? So for example, you start out, if you've got x and y, you start out at a and g, the arithmetic and the geometric mean get started out as x and y. Then you compute the regular arithmetic mean, which you are all familiar with. The mean of two numbers is you add them together and you divide by 2. The geometric mean is you multiply them together and then you take the square root. Right? As an example, suppose that we have 24 and 6. It's got a built-in test case over here. Initially, it's going to be 15 and 12. Then if you do this again, you take the 15 and 12 and you plug them back into the formulas above, right? 15, 12, that becomes 13.5, and then the other one becomes 13.41. If you do this over and over and over again, they start to converge on each other. After 4 iterations of this, it looks like it agrees in the first, 13 decimal places or so? And then it agrees almost in 20 decimal places or whatever, right? And eventually it'll get down to convergence, but that convergence might be infinite, right? That you have to do this an infinite number of times to converge on the actual number. We're not going to do it infinitely. We're going to do it when it's close enough, right? And when is it close enough? Well, we can define that. As long as it's within 0.000001 of each other, that's when we'll stop, because that's good enough, okay? All right, arithmetic and geometric means. Let me come over here, and let me go ahead and copy demo into agm.c, and go ahead and get rid of this. And sometimes you have to refresh, remember. There we go. Is there one built in the math library? Great question. Let's do that. Over here, rubber duck, debugger. Does the math library have an arithmetic geometric mean function? And the answer is going to be no. Does not have, but you can do it using basic functions, right? Okay, thank you very much. All right, so I'm going to go ahead and update this to compute the arithmetic geometric mean of 2 numbers, right? C, and here I'm going to show you something new, Wikipedia. Okay. There we go. What I'm going to do is I'm going to grab that link and I'm going to put it right here. What did I just write there? href, what is that stuff? That's HTML, right? When I take this over to Java, that HTML will now be linkable because I'm using proper doc style comments here. All right? So get into the habit of using doc style comments because you can do things like that. Okay? In fact, it's linkable here right now. If you just hold down the command button, maybe the control button, and then it'll take me right there, but I'm already there. Okay. All right. So we are now working with command line arguments. So let's go ahead and read in from command line arguments. I'm going to make a check here, just a rudimentary check. If the number of arguments is not equal to 3, why 3? Yeah, the first one is the name of the program, and then I've got X and Y. All right. If it's not equal to 3, printf usage is going to be, here I'll show you another trick here, X and Y. %s is going to be a placeholder for a string. Remember that argv sub 0 holds the name of the program. So the usage would be a.out x, y, right? And it tells you how it should look. Otherwise, I'll go ahead and exit on them, okay? Not absolutely necessary that you do this in your programs, though. Right? It is going to be necessary now that we've covered conditionals that, like in this week's lab, and definitely in your hack this week, you need to be doing basic error checking. Right? So did we get enough command line arguments? Yes. Double X and double Y. Why did I make them doubles? The example we had was 24 and 6, right? But eventually they're going to be doubles, so let's just go ahead and go with X and Y here. How do I convert the first user-provided command line argument into a floating point number? A to F. Good. And the second one would be A to F of 2. There. Now I've got X and Y. Oops. There we go. Get rid of the duck debugger. All right. I'll go ahead and jump down to the end here and say return 0, but I'll also print out printf the AGM of %f is equal to %f, end the line. X, Y, and then we'll come back to this because do I have a value, do I have a variable yet to store the AGM? Nope, not yet. All right, help me out. I've just got X and Y. And again, when you're trying to solve a problem, you generally want to whiteboard it, right? We've got a whiteboard up here, but it won't show up well on the on the live stream here. So we'll use my IDE, the VS Code here, as my whiteboard. But also, we've got a built-in whiteboard solution here, right? It walks us through each one of these steps, 24 and 6. What you do is you add those together, you divide by 2. You multiply those together and take the square root, and that gives you A and G. So let me go ahead and create A and G over here. Double A is equal to double G is equal to. So what's the arithmetic mean? 1/2 of X plus Y. What's the problem there? Yeah, 1/2. What happened in your second lab when you did that, or what we gave you the code that did that? It's always going to be 0 because of integer truncation. So 0.2, right? Or you could just go ahead and say divided by 2 if you wanted to. That'll work because X plus Y is already a double, so 2 doesn't need to be a double. I'll just go ahead and do it this way. Okay. How do I do the square root again? SQRT of X times Y. All right. And we could go ahead and print those out, right? We can go ahead and print out A and G. A for %F. And let's just see, we don't have a loop yet, right? Oops, GCC AGM, right? And then what else do I need to do on Ubuntu because it's not configured correctly? There we go. A.out, and we'll go ahead and use what's in Wikipedia, 24 and 6, because I already have a built-in test case, right? I have a test case that was given to me. So 15 or 12? Okay, well, I'm assured that that first iteration worked, 15 and 12. Let's do it again. So instead of writing a loop, I'm going to initially just copy paste. Now I can't redeclare it, so what I'll do is I'll go ahead and get rid of that. Is this actually going to change though? No, why? Because what am I printing? A and G, and that's always in terms of X and Y, X and Y. So let's change the second one here. What should it be? A plus G, and this one should be A times G, right? What I'm doing is I'm generalizing one piece of code. I'm generalizing it so that I can then put it inside of a loop and it'll work on every single iteration, all right? Now let's see if that worked. Remember that at this point it should be 13.5 and 12.72, is that right? Ooh, yeah. 13.5 worked, but the second one didn't work. Why? Yeah.
You changed A in the first.
Yeah, on line 26, A has already been changed. It should have been in terms of the previous A. Right? So I'm thinking I probably need another set of variables. Right? Let's come back up here and say double A previous, G previous, right? Double B current, and, or not B, but A current, and G current. Right? Now I've got two sets of variables. The previous one that I need to calculate the next, we could call this next instead of current, but usually you have previous, current, and then next if you need all three of them, but we only need two. Right? All right, so initially, what's it going to be? The current is going to be X, and the G current will be Y. Right? All I'm doing is saving these off as the original variables so that I can actually print them below. Right? Okay. Now, how do I want to proceed down here? Right? Let me go ahead and get rid of this now. The current is he actually probably wanted to do, that's all right, we'll go ahead and figure it out here in a second. A current is equal to 0.5 times A previous and G previous. Right? The next one will be in terms of the two previous ones. And likewise here, that this will be changed to multiplication, and this one ends up being G current, okay? Now I can put that into a loop, right? Actually, there is still a bug here, but that's all right, bear with me. There's still several bugs actually, intentional and unintentional. Right? There we go. Why did I immediately jump to a while loop without even thinking? Yeah, are you going to do this 5 times? Are you going to do this 10 times? Are you going to do this 100 times? Right? When are you going to stop? Well, first of all, can a double really have that much precision on their numbers? No. So a double is only going to have precision to 17 decimals of accuracy. So what I'll do is I'll say while A current and G current are not close enough, ... continue doing this operation. Now, what is not close enough mean? Let's translate that to math, right? If I took the difference, right, that means the difference between them should be small if they're close, right? So I want to be careful here, though, because what if one of them is positive and one of them is negative, and one, or vice versa, or they're both negative or something like that? Do I really want to take the difference by itself? I want to take the absolute value of those two things. Okay? So while the absolute value of those two things, and there is an absolute value, right, of the difference between those is not close enough, in other words, it's greater than some tolerance, then continue. What should that tolerance be? Well, we define that, double. Tolerance. How tolerant do we want to be? If there, how about 10? If it's within 10 or 100, right? Then what's the arithmetic geometric mean of 25 or 24 and 6? It'll end up being 24. That's no way. Nope. So we want it to be very, very small. Now I don't want to put in a million zeros here and say 1. Actually, you could do something like that, but that's close enough, right? Whatever I did there. If it's within, this is like tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths. Maybe that's even too much. I'll go ahead and go down even more. If it's within a 1 millionth of a decimal, then it's close enough. Okay? So while the absolute value of those two things is greater than that tolerance, I keep going until one more. Let's try it. Oops. Oh, and by the way, if they're close enough, then does it matter which one I print out? I'll just do that one, right? And then get rid of the second one here, because they're close enough. All right? There we go. 24 and 6. It's 0. Is that true? No, it's 13 and change. All right. I'm going to focus first on this line right here. Abs. What is that good for? What's that short for, first of all? Absolute value. Let's ask the rubber duck debugger. I'm using abs, but I'm getting 0 results. 0 as a result. I don't know how precise we have to be with our language with the duck. But sounds like you're having trouble with abs function. Could you show me a come on. I'm taking the difference between two doubles. All right, there we go. The abs function is designed for integers, not doubles. For doubles, you should use fabs. The F is float, right? Now, this is something called function overloading. It's something that C does not support. and other languages do. When we move this over to Java, we'll see that we don't that there's only one abs, right, method. Actually, there are several methods, but they all use the same name. That's called function overloading. But in Java in C, we don't have that. As a consequence, we have to have actually several different absolute value functions. We have fabs, labs, abs, lalabs, right? One for floating point numbers, one for integers, one for long integers, et cetera, right? So we have to use fabs in this case. Let's see if that fixed our problem. Okay, still 0. Right? That was a problem, but it wasn't the problem, the only problem. Yeah, okay. Well, current was x and y, initialized x and y. But now let's walk through this. In fact, you know what? Let's go ahead and go with, I showed this before, Python tutor, or did I not? Maybe I didn't show it to this section. So I'm going to show you another tool here. All right. There we go. And this is available on Canvas. But what I'll do is I'll try to visualize this execution to find out what's going on here. What are you complaining about? I can't, oh, come on. I can't use math. It's right there. Undefined. Oh, I can't believe it doesn't work. Oh. Whoa. It doesn't automatically bring in the math library or use those flags. Okay. Fine. Let's try it with C++. There we go. All right. Here's a C++ is just a superset of C. So any C that you write can actually be compiled by a C++ compiler. Right? It's just C. When you write C++, you can actually write C and not use any of the features of C++. All right, so let's walk through this. All right. So yeah. Oh, you know what? This is gonna die. All right. What I'm going to do for this particular demonstration is I'm going to take that out and I'm going to hard code these to 24 and 6. There we go. All right, now I'll be able to visualize this. Right? All right, so because it doesn't work well with, it doesn't play nice with, okay. I don't know why it jumped all the way there, but anyway. All right, so let's walk through this. X and Y take on the values 24 and 6. Tolerance takes on that value. All right. A previous and G previous are never initialized, and so that's why we have question marks over here. And then A current is equal to 24, G current is equal to 6. Now, the absolute difference between those is going to be 18, which is strictly greater than the tolerance. So we will execute this loop. Now we're inside the loop. See that A current ends up getting that value. Oh, yeah. Did it end up getting any values there? Nope. So the current is done with respect to the previous. All right. So let's come back over here. What should we be doing then? On that first iteration, we mistakenly made X and Y. Well, we can go do them to both, but they definitely need to be initialized. The previous needs to be initialized to X and Y. All right. We're still not done here. All right. Let me come back over here and make that fix as well. Edit this code, and I'll just do equals X, and then this is equal to Y. All right. And then visualize this. Okay. So, nope, let's go all the way to the beginning. Right, I don't know why it's jumping into the middle of the program, but in any case, we've got 24 and 6 now, okay? Watch as 24 and 6, the previous values are not touched, right? They'll retain 24 and 6, but you'll see now that it gets 15 and 13 or 12, I guess, all right? Is that correct? 15 and 12, and that is correct. All right. So we come back up here. 15 minus 12 is 3. That's strictly greater than the tolerance. So we're going to execute this while loop again. But what happens in this while loop now? Read line 25 to me. The current is going to be set to the previous. Did the previous change? Nope. So actually, what's going to happen here? Right? An infinite while loop here. Note here that it even caught it. It stopped it after running 252 steps since the trace is growing too long. Shorten your code or make your even this is not able to determine that this in fact is an infinite loop, right? It just ran it for a long enough to say, okay, I can't go any further. It's not actually detecting the infinite loop there. What do we need to do with these four numbers here? We have to reassign them, right? I'm gonna compute the current ones from the previous ones, but then I need to set myself up for the next iteration by taking the current ones and placing them into the previous ones so that the current ones can be recomputed. So let's do that. After I've computed them, A previous is updated to A current, and G previous is equal to G current. Right? Let's try this one more time, and I'm pretty sure that we've got all of our bugs worked out here now. And oh, nope, darn it. All right, so now I don't know what bugs I've got here. Yeah, go ahead.
Your current variables aren't initialized when you go to the while loop.
Ah. Oh, maybe I should have changed these instead. I'll just go ahead and keep it at X and Y. I'm going to just go ahead and initialize everything here. All right, there we go. All right. There we go. 13.45817. 458171. 458171. And that looks to within a million to me, right? We could print out more significant figures and see if where it starts to disagree. We could, of course, change our tolerance here to be much, much more. But then we're not printing out enough to see if it's like, if it even matters. It's got 17 decimals. Come on, there we go. 4817, is that the next ones? 4817, 256, 1595. All right, and at that point we lose our precision, right? So, yeah, it's close enough. Right? Is that the only test case that I should do? No. What's another easy test case? 6 and 24, right? Does swapping them screw us up? No, we still get it. Another easy test case would be if they're equal, 10 and 10. What's the mean right there? 5, and what's the geometric mean right there? I mean, square root just cancels it out if you're squaring something, right? So that should be 10, right? By itself. Right? Take 10 plus 10 is going to be divided by 2, right? What other things that should we test? What's another corner case maybe? 0 and 0, right? Or 0 and 10, right? So there we go. Is that correct? I have no idea. Right? How could I design a test case besides these trivial ones? Use a calculator. Of course, you could pull out your own calculator and then write it on a piece of sheet of paper or something like that. Or you could go to another well-known calculator and just say AGM of blah and blah. So 1320.16, and I'll come over here, paste, without that comma, 1320.168, blah, blah, blah. Right? So when you're designing test cases, there are easy ways of designing test cases, and then there are, this is not cheating, right? Use another tool to design a test case like this, an online calculator or something, right? You're not cheating because all you're doing is verifying that your code is correct against a standardized implementation like this. Okay. One other thing that we could test is negatives. If one of these is negative, unfortunately, what happens with negatives in a square root? Yeah, imaginary. So we might have gotten lucky in this case. I'm not sure, but I don't think that it's defined. So if you come back over here to the reference, negative, right, negative, but not positive, positive. There we go. In mathematics, it's defined for two positive real numbers, x and y. So it isn't even defined technically according to this reference here. So what we could do is we could go back and add some additional error checking. If they enter either one of these as negative, if x is less than 0, or if, how do I do or again? Two pipes, right? Or y is less than 0, then printf not defined for negative numbers. There we go. And here I'm going to exit on them with a different error code. Up there, error of type 1 meant that they didn't give us enough command line arguments. Here, an error of type 2 means that they gave us bad command line arguments. Right? At least that's what we're doing here. Right? Not defined for negative numbers. Right? So you can take care of a whole set of bad inputs by simply just rejecting them. Right? Yeah.
Is there a way you can check and see like which error code you get?
When we talk about error codes, yes. Error no. There are standard ones. Error no.h. There we go. There. Error code of type 1 is operation not permitted, EPERM. IO error would be 5. The only ones that are actually defined are EDOM and ERange by the standard. That's a mathematical argument out of domain. In other words, like square root of, ERange, square root of -1 would be I, which is not in the range of numbers. And then domain would be a bad input, basically. So log of 0 would end up being a EDOM, I think. But most of these you'll never encounter. Most of these are like lower level system stuff. If you were doing systems programming, you would deal with these. The ones that I'm using over here are user defined, right? 1, 2, 3, 4, whatever, right? So it's a completely different set of error codes, and we'll define our own error codes later on.
Is there a way you can like check that, say if you need to like test something like that? Like you see the error code you get?
If you want to do it from the command line, yes. So let me go ahead and do this and echo, I think it's $?
Okay.
So we got a 2 out of that program. If I did, say, only one command line argument and I got that, then I got a 1 out of that program. If I did it correctly, let's do it like this. I don't know. There we go. Then what's the error code that was, what's the exit code? 0, right? So inter-process communication, yes, you can do that. But within our program, we're going to actually do it a different way. When we write functions, those functions will return error codes. And then after we've called that function, we can say, did it result in an error? By looking at that error code that it returned. Right? But yes, the $? Will tell you what the exit code of the last program that you ran was. Right? Like ls foo. All right, so there is no foo, so what did ls output here? 2. And now that does not correspond to this guy up here of no such, I guess it does technically. So apparently, yeah, that's what 2 corresponds to. I don't know how to get it to fail any other way though. Good question though. This is all bash programming here and command line programming and stuff. Any other questions? Otherwise, when we come back, we'll go ahead and continue with some more practice. All right, see you on Friday.